So last week we started with this idea of determinism, and then we've moved to probability theory, statistics, and so on. And I'm going to continue in this direction. But I thought maybe I need to have more focus on these topics of statistical measures, just very quickly. And then today, as you remember, in the last part of the meeting, we talked about probability densities, and then we said in many real cases you don't have these data sets in practice, so it's not always ideal forms and so on. So we said we have the notion of density learning or estimation, and today I will talk about it quickly, and then I will mention the notion of meta parameters. This is very important. I mean, you will know this for sure later, but this is what you always hear. Sorry. This is what you hear always, and this is an important notion. And then we will go quickly from density-based, which is a kind of unsupervised way of unsupervised learning problem. In fact, we go to regression problem, which is again a kind of essential and fundamental problem in everywhere. These are very fundamental. And then I will talk about least square methods, and then we will end up with this method. These are more or less very basic statistical machine learning methods or machine learning methods that you need to know, but most of the cases in reality, as you will see, they have limits, so we can't use them, but these are like foundations. So I would like to focus a bit on this notion of statistical measures. If you remember, I said we have, for example, mean has a statistical mean value or average, that's what we call as average, has a specific meaning as a mathematically. Then we have notion of variance, and then I said the idea of higher order statistics, which can be modeled like this, that these are your observation data sets, observed data set, and this is, for example, if it's the mean, the arithmetic mean, always this value is 0. And then the question is that if k is 1, then it calculates the mean. And if you fix the mean and now go to higher orders, they're talking about different aspects of this distribution. For example, imagine this is the distribution of the data. Then you can calculate, by this formula, you can calculate the mean value, you can calculate the standard deviation or variance, which means what is the expected fluctuation around this mean. And then if you go to higher orders, up to 4, you can interpret it, but if you go further, you can't interpret it. What does it mean? For example, for 3, it means this factor called skewness, which means that where is the direction of the tail? This is important. For example, if you have the distribution of income, or if you have the distribution of age of people and so on, you always have this tails, and then you have this average and so on. So the question is that when you have a data set in statistics, you want to find quantitative measures to measure different aspects of these things. In a way, it's kind of shape. And if you go to order 4, you have the compactness, or in principle called tailedness of these factors. So if you remember last week, we had this idea. For example, here I'm calculating the first momentum, which is here. So for example, imagine I don't know how to calculate the arithmetic mean, which we know based on our high school studies, but here if I move the location of this red dot, you see this sum is changing, and in one point it's 0. So this is the meaning of this mean. So what does that mean? I mean, you can interpret this from physics point of view, that these points are attracting this red point. So it's a kind of competition, and in one point you have the stability. So this stable point or equilibrium point is the point that you call mean value. So you can do this for all the other orders. For example, now I want to play with that, and it gets a bit crazy that you can't explain as well, including I can explain it as well. That, for example, you have this two-dimensional data set, for example. Now imagine we want to check if you have a grid in this space, which areas are effective, how each point is affecting which of these measures, these momentums, for example. So if I do that, in principle, I'm creating a grid in this area based on the minimum and maximum, and then for each of them, it's like that I'm moving this point, and then I'm calculating the momentum, first momentum, second, third, and fourth momentum. And you can imagine this case as a case that, for example, you want to locate, for example, an airport, or you want to locate a warehouse, you want to locate a buffer location in your workshop or whatever. So you want to see, I want to calculate the distance. If you look at the average distance, you get the mean value. This is the best result. But if you care about the distribution of this, for example, if you want to be, equal for everyone, then you should look at the variance. And then if you want to be equal for everyone, then you should look at the skewness. For example, look at here. For example, if you put the location of that spot in the mean value, there are some points based on, this would be, for example, the distance to that point. There are many points that they should walk a lot to reach to the, for example, to the warehouse or whatever, or fire station or anything. You can think about it. So the question is that if you want to play with this space, how these functions are behaving, for example. In this case, think about it now. This is the data. Now this is the field. It says if you want to minimize the first momentum or average, the area that you get the best result is this. If you want to minimize the variance, this is the area. Red means high value, blue means very low value. So in principle, it says if you go to this area, there are many of these points that they should walk a lot to reach to this point. So in principle, the diversity and the variance is increasing. But it says if you go to this direction, you're playing with that in a different way. So this is a safe area. You can move, and then because of that, everybody is walking the same distance. This doesn't mean that everybody is walking less. It means that everybody is walking equally. So if everybody is walking 1 kilometer, it's not a good answer for you, but it means that the variance is very small because everybody is walking similarly. So I want to say that what does this momentum means? I mean, imagine if you have a kind of optimization problem, if you use any of these momentums, you will get completely different answers, or if you combine them. And sometimes, for example, there's a field of, for example, facilities location problem, that this is called some kind of balancing objectives, that you don't care only to minimize the total distances, but you care about the how to say, the justice in it. These are the kind of justice parameters. And then if you go to further orders, it's not that easy, and you have these kind of crazy contours. So it's very interesting from one point, and then I think in physics there are people studying these kind of momentums, but at the same time it's not easy to interpret that. And as I said before last week, this field is extremely limited to very simple methods. It's usually a variance and average and so on. And if you increase just the momentum, for example, in this case, it's not that easy to interpret. And in principle, this is the area that statistics is struggling, because as I said before, in statistics, again, similar to deterministic ways of science, you always try to find some rules and you try to understand things and so on. And in machine learning, you try to always bypass this kind of questions. So this was like the remainder of the last session. And if you go to now what we discussed about density functions, if you remember, if you don't remember, I will show you here. We discussed about these are called probability density functions. These are all idealized density functions. Like this is a normal density, and then you have, if you remember, we had different kind of functions here with these kind of equations, yeah, and discrete and continuous. But then we said in reality, usually we don't have this kind of ideal pattern. So we have something like this, and it's not just one. So this is the first part. You just start to learn this, the so-called you estimate these functions. So imagine you have this kind of data sets, which is very ideal for your observation in any case. So you have a well-shaped distribution, and then you can easily fit a Gaussian distribution. But if you have this one, in principle, you see immediately that there is not just one Gaussian distribution that you can fit on that. So in principle here, for example, with the idea of kernel density estimation, we make a trick, and we say, what if we just assume that each observation is a kind of random variable, is an event from a random variable with a certain ideal distribution. So we just simply assign one normal distribution or any distribution to any of these observations, and then average. And then I think you will see that I think if you are using, for example, Adobe or any of this software, already this kind of blurring. They're all working like that. You just have some data set and then you're just doing some kind of smoothing. And these are very essential and very powerful concept and I think from very simple methods in machine learning to up to this deep learning or very complex computer vision problems, you need to know them, and they are always there. And this is the beautiful thing with that. So the first thing that in principle, if you don't need to have a model, for example, if you just want to have a pure data, that database approach for probability estimation, you usually use a histogram, and this is a model with no generalization. So I think you all know what is a histogram, and then you just define a beans, and think about it that you simply just do averaging in the local areas of observation, and then from your data set you go to this. So then you have this pattern easily, and there is no model here, it's just pure data, right? And of course you have some assumptions how to cut this space and then do the averaging. But then you say it's noisy. How you can remove the noise? Imagine this is your point cloud. How you want to make a smooth surface? So there's a very simple trick that you just assign a kernel function around each data point that you are observing. This kernel, imagine, is a kind of Gaussian distribution, and in principle is a non-negative function that integrates to 1 over its domain. So like all the other probability densities. So I will show you what happens here. For example, imagine you have these data points. I only have 8 points. And then you assume that I don't think that this data is a result of a deterministic process. You think that there's a randomness behind that, right? So in principle, you say, instead of fixing this point, what if I assume that next time there might be some observations around this point with some normal distribution. So what you do is that in principle, let me see, okay, this is your data set, and then you simply apply these functions. This function here, we use a Gaussian distribution, which is, I wrote it here, is this one. So you have this U is the data point, and then you have this domain, for example, from let's say -2 to 6. So for each of these points, you set a Gaussian distribution, and then you say the center is the observation, right? So then you create a value. And there is an important factor, which is H, which is the so-called meta parameter. You should to select it. This is like a standard deviation. If you make it small, then you have no variation. If you make it big, you have variation, right? So I play here with that. Like if it's 1, you have this, though in principle they don't affect each other. But if you increase this, you see that these Gaussian distributions are like this around each observation point. And what we get here at this blue line is simply summing over them. It's nothing more. And by that you have this beautiful and smooth pattern, which is not any longer noisy like the original histogram. So you can play with that, and you will see how this blurring happens. So imagine if you have a peak picture, you can play this with the colors. You have RGB, for example, or if it's PNG, for example, is one color or whatever. You just simply do this in a local area. And I think this is already implemented in many of the software that we know, right? This is everything like that. It's extremely simple. Still, you need to know what is this Gaussian about. You have these assumptions that this data is not deterministic. Because of that, you think that next time that you have number 6, next time might be 6.2. So in principle, you have this likelihood with the maximum likelihood for the center, and then you play, and then you can make a parametric model out of that, right? So this is a one-dimensional case. Now think about it that you can have like 100 dimensions. So there you might have some problem. But in principle, everything is the same. There you just multiply these Gaussians in different dimensions together. But in each dimension, again, you have one Gaussian. And then always you have this meta parameter. So then you might ask, okay, what is the maximum or what is the optimum bandwidth? The short answer is that nobody knows in principle. It depends on the data. These are the so-called meta parameters that you need to learn. For example, in any algorithm that you use, always you have some meta parameters like number of loops, learning rates, architecture of your model, and so on. So, but there are some methods for that, and there are people working on this to optimize this kind of bandwidth. For example, there are lots of rule of thumb methods, and there are functions that you can minimize some error functions that we will see now later in a regression. What does that mean? And then usually you can do this with cross-validation, for example. For example, you can take some part of your data. This is the meaning of cross-validation. And let's say out-of-sample validation, that you have test data and training data. You do optimize these models with your training data, and then you implement directly this to your test data. And you can see how good is the result. But yeah, I think it's open in principle. And this is what I implemented here. So in principle, if you remember, we had all of these functions. You can try and just play with that. You will learn it much better. You can replace any of these. You can replace this Gaussian inside this Gaussian with any of this distribution. So it will create different patterns. So I think you have heard about this kind of blurring, or this kind of, if you are working with image analysis, there are always lots of functions like this. You always just change the kernel and the bandwidth. So if you can do it, you can write it down easily for yourself, that you take the image and then you do this kind of smoothing or something like that. So, but in principle, in machine learning, in the applications that you have with working with a real data set, usually don't need to write it down because it's very slow. So I think I introduced it before, but now again I would like to mention, you should definitely look at this library of scikit-learn. It has almost all the classical machine learning methods implemented in Python in a very nice environment. So it's extremely simple to use it and play with that. So for example, you can start with this kernel density estimation and then change the kernel, for example, and see what happens. But the idea is nothing more than forgetting about the determinism, and second, summing over these Gaussians or some kernels. And most of the machine learnings at the end are like this. If you step by step learn like that, it will be at the end the same. So for example, now imagine I have this data set. It's a two-dimensional data set, and you can easily fit a kernel dense a model to that. Let me find it first. Where is it? Okay. For example, here I'm using, I guess, SciPy. SciPy is another library. You should definitely look into it. So you just say stats. I think I imported. Yeah, I assume that you know Python. So I just imported this library, and then I feed my data, and then, for example, you get the model out. So here you have one section of one dimension of the data in the same data set. Oops, I think something is wrong with the data. I don't know where. Okay, maybe I should change it here. So you have this one, and if you visualize it in a 2D, you have this kind of contour diagrams. So what happens is that here you just learn this space of probabilities, but it's not any longer based on one idealized equations. But then you can use these, as I said before, for smoothing and manifold learning, which is an important concept. Or you can use it for resampling. For example, if you have few data set and if you want to generate new data set, now you can think about it. You can take this space, because it's pure quantitative, right? You just give the weights based on these probabilities for any area. For example, you just want to generate new data set which follows this distribution. So you don't want to do the real experiment any longer. You can use these learn functions. So but definitely this is very simple method. In most of the application you don't use that. I mean, there will be more complex methods that I will explain later. I mean, in next sessions. So you can use for resampling, you can use it for clustering and pattern recognition. In principle, you can assume that there are, in this case, I have like 1, 2, 3 main clusters, and then I have these 3 subclusters. So one session will be about clustering, and you will see that they're completely related to each other. If you cut this space now, based on these contours, it's a problem of clustering. You just want to do your data clustering. So you can use the same method and then just cut the contours. If you don't cut it, you keep the continuity, you have the probability density, and they are all related to each other. So you can use it for prediction, and this kind of prediction that you can generate random results, because if you have a function which is deterministic again, it always gives you the same results. But with this kind of method, I will show you quickly. For example, here you can easily create a prediction function which generates some kind of random results. And this simple idea, later you will see, for example, let me see here, like for example this model, which is a kind of, as I told you in the first session, is a kind of sequence to sequence model, which is very powerful generative models to generate hand drawings in a very good quality. Here you have, just here, these small boxes, you have these Gaussian mixture models, or this kind of learned densities. And what happens here is that you learn a function that, for example, x, in this case we visualize it as one dimension, but this x could be at 1000 dimension. And then you condition your output, which is y, to this x. And since you have learned this function, it tells you that y in this x could be any of these values. So in this case of, for example, I don't want to go through it, but in case of, for example, very fun example, for example, would be you want to generate this kind of things, which I don't know is a good application or not, but it's interesting to just, for example, for example, you want to say, for example, if this is an input, can you generate something similar? And this is exactly very unique kind of generative models if you have probabilistic functions. If you have deterministic, it's always the output is the same, right? And the beautiful thing with this method is that it's like this. You just say, what if x is this? And this is a matrix, right? This is a vector. It can be a high dimensional, it can be a picture, for example. You can condition this space that what if I see this as a picture and this sound, then what would be the outcome? Then this tells you that this is the possibilities. Here it's not likely, but this area is very likely, for example, this area. So then it can generate something like these pictures. We will see this, I think in 5 sessions we go to this kind of applications, and you can do it, for example, easily. You can implement it. But the concept is here, and it's not more than that. Just summing over local Gaussians. So I think there should be a limit, but okay, there is another problem here, is that this idea is very cool, but there is a very fundamental problem here, and because of that I told you this method doesn't work in principle in reality. And this problem is called curse of dimensionality. The problem is that if you have like one dimension like this, with few samples you can fill the space, and then when you guess in betweens you don't have empty spaces. But now imagine you have 2-dimensional data set, so you need more data sets to fill the space. And if you have 100,000 dimensions, for example, which is possible, then even with big data your space is extremely empty. So you can't use this concept of Gaussian kernel because the space is empty, everywhere is empty. So this method becomes completely useless. So later you will see that, for example, why this notion of deep learning is working, if you know these terms, that we will talk about it. Like this method is based on this deep learning, for example, beside this cats that I show you, right? So you will see that how they are reducing this dimensionality in order to use again the same method. So the whole trick is always how to play with this space. But if you literally take these simple methods, they usually don't work in higher dimensional space, because you know that this curse of dimensionality, if you increase to 3, 4 and so on, the demand for data is increasing exponentially. So you're always in a catch-up process. So you can play with that, but it's most of the time useless, right? And then prediction, I told you, sorry. So this is from another point of view. Think about that x and y relations. This is a kind of, when you learn these x and y relations together, in machine learning this is called unsupervised learning, because you don't have a certain target. You just want to learn this density space. But what if you just say, no, I want to learn a function that always predicts the price of a house. I want to learn a function that always predicts the next move of my robot's tool, for example, head, right? So there we are moving from unsupervised problem to a supervised problem, that you always have a target, and then you learn your models based on a target. And this is the classical definition of regression. For example, you have X and you have Y. Definitely you can use this kernel density estimation on this data, but that's not the case here. You want to learn a function that when you give the X, it tells you what is Y. So again, it can be probabilistic or deterministic, doesn't matter. If we use it in a deterministic way, we have a linear regression. So think about it, that how you want to approach this problem, how you want to learn this. In classical physics, you always have some equations, and then you know the mechanics of the thing. And then, for example, you have Newton's equations, whatever, and then you just adjust your parameter. But here, sometimes you even don't know which parameters, which factors are important, for example. Like, for example, you can do a lot of crazy and fun things. Like there was, I didn't find this application, but there was a guy who find a large database of data sets of many things. For example, number of people graduated in civil engineering, number of ice cream sold in this month, everything, right? So then you have a lot of dimensions. And then the question was that with this machine learning, is it possible to find correlations? And then, for example, there were a lot of fun correlations. For example, number of graduated people in civil engineering was correlating up to 99% with the number of damages in the bridges in the world. So this kind of crazy things. And that's the thing that again goes back to the original story that we talked in the first session, that question matters. Because now you don't have any equation, but you just want to find out if there is any relationship between anything to anything. And then in the supervised problem, you always have a goal. You just say, I want to know, for example, if I drive a car, if I can predict the price of a stock market, if I can predict something, right? So you have a target, and then you feed a lot of variables. So there is no equation. This is very important. So the idea again is very simple. Thanks to these guys, Legendre and Gauss, in beginning of 19th century. The idea is that they simply said, forget about any natural description of the phenomena. Just think about it that you have a set of data set Y, which is important for you, and then a lot of observations X. So what if we just tune and feed a function to this data set? And how do you do that? For example, in this case, you have something like this, that you have Y, and then you have a linear regression of order 1, which is, it says that you have only 2 parameters. If you learn these 2 parameters, you can cross a line, right? So this guy said, let's like this momentum that we discussed before, let's calculate the difference of our function. Let's start with some beta values, just arbitrary, and then this function produces some results. So let's calculate the difference. This is, if you remember, this is the second momentum, right? Over these functions. Now, in this case, as I showed you, I think this was a bit more vague here. But here I'm just searching this space. I say, what happens if I select this point as a parameter? Now, in the linear regression, the first and simple case, we have 2 of these factors. So in principle, I can start choosing by, for example, randomly these 2 values, and every time I have a line, which is a function. And then I calculate this error, which is called squared residuals, and then I try to minimize this function. For example, here I showed you that which area of the space you get the minimum values, right? Based on this, for example, this one. So if you can now parameterize these functions and then learn these functions, then you're in the area, for example, in principle, machine learning. So again, all of this machine learning, it's important which kind of the so-called loss function you are trying to optimize. So the way you are parameterizing your model and the way you're trying to find the best values. Here, for this case, apparently there's a closed form result for that. But in general, if you increase the orders, there are a lot of optimization methods for that. I don't want to go through it, but in principle, just think about it that you have this kind of degree 2 functions, and you want to find the minimum value. So in principle you have 2 parameters, not more. So I hope there is an interactive version of that somewhere. Okay. So if you think about it like this, oops, sorry. I think I need to run this first. So think about it that now I have two parameters, A and B. I call it A and B, and then this is my first guess. And literally with computation we do this, right? I'm just changing this, and then this is a value called bias, and then you see what happens. These lines are the distance to this, the shortest distance to this line. So these red ones are the shortest distance to this blue one. So in principle, this error that we are minimizing is to minimize this distance. So again, from the point of view of physics, you can think about it that you are trying to minimize an energy. So you have an energy function here, and if you find out the best parameters, this is the area that you have the minimum energy, or the most stable area. So in some of the simple cases like linear regression, you can easily find it with a closed form, and analytically in many of these applications, imagine this function could be a deep neural network. So you have a lot of layers and so on. It's not easy to find a closed form, but there are lots of repetitive algorithms. So in principle, in most of machine learning algorithms, you will see that later you will have something like this. And then the algorithm, the contribution of the algorithm is to find a way to find the best parameter set. The moment you find it, then you say, okay, I'm done. Now I can predict. And then you reduce this space of the observation to one line. So in a way, it's a very interesting engineering problem, because you are reducing the amount of data as well that you need. Because if you have a lot of observations, from now on you just say, I want 2 parameters, and this is nothing more than that. And imagine in terms of compression of information and so on, how much efficiency you have now. So, but there are fundamentally, I think, important issues here that, as I said before, the underlying idea behind this least square method is the essence of many of machine learning algorithms, if not all. I would say all of them is based on that. And the fundamental change that we have is that this is where we have an inversion in the modeling process. From designing the model with the question of how, now we just say what we expect to see. And this is exactly implemented in this equation. We don't know how these parameters of this function f, and think about this function, it could be a complex anything, it would be hierarchical and so on. We don't know how, but we know that we want to find a very low error. So we just impose this to the model, and this is a completely different approach to non-machine learning methods, because you always start with some theoretical models and then you try to see how good you are. Here you just say, I don't care about these parameters. And these are full fictional. They are not real. This function is not real any longer. This is a mathematical function that somehow correlates with your problem. And the problem is that if you think about this as a natural way of a naturalization, that's the problem, because most of the observations we have in many fields like medical studies and so on, it is possible that people come back at the end of training and say, okay, let's naturalize these functions and try to interpret why this linear regression is correct. Here, this is a fundamental mistake, I would say, but still is mixed. You will go and you will see that most of our studies, for example, published in, I don't know, Nature, for example, you will see that they say, we found these parameters, this is the essential functions for, I don't know, for cities, how they are growing and so on. This is absolutely wrong. Here, the whole idea is that forget about the mechanisms, because it's complex. Of course, you can spend time on that. But here with data, you just learn a mathematical function. And that's the beauty of that. You don't need to worry about it. It's not a black box. It's just your tool. You just say, I feed something which works like that. And if it doesn't work, you will realize that through your data. For example, I'm doing this now for a while for predicting real estate market price. And then we will see this. I'm using this kind of random forest here for this function with a method. And I can predict the real estate price in Switzerland up to 95%, but I don't know why. And then the classical method, which is called econometrics, they always try to know, for example, in this region, room is important, the number of rooms, and in this region, the location is more important. So they're always trying to make mechanical models of the reality of the real estate market. Here you just say, I want to fit. And then every week, imagine I'm updating my model. So in principle, this is for some people, the scary part of machine learning, that they say, wow, it's a black box. But here it's not black box, it's an intellectual decision that you say, okay, but there are infinite number of models if you want to go to any applications and build a descriptive model for that. Here just give me the data. This can be stock market, this can be real estate, this can be robotic motion planning, or anything. Just learn this by the data. So this is the power of that. And I think this is a breakthrough in this time by Gauss. And then, for example, for the first time, this is a very interesting story, that for the first time there was a guy, we can read it, an early demonstration of the strength of Gauss method came when it was used to predict the future location of the newly discovered asteroid Ceres, or I think Ceres, on 1st January 1801. And the Italian astronomer Giuseppe Piazzi discovered Ceres and was able to track its path for 40 days. So these are maybe the initial application, the first applications of data-driven modeling. So this guy was able to take a photo or observe the location of this asteroid for 40 days. So one way would be, from now on, they want to know when again they can see this asteroid. So the classical way in that time was to use the so-called Kepler's complicated nonlinear equations of planetary motions, like what we discussed in the first session, I think, or last week. And the other guy used this least square method. So simply, he said, maybe there is a relationship, but we don't know what, but we just learn it by this. So this was the first application, then it works. And then that time Gauss was 24 years old. And this was a breakthrough, because imagine, it's very strange if you say a lot of physicists know all of these equations, and then you just say simply, we don't need to know the equations. So imagine what would be the effect. And nowadays you can go to different fields with machine learning, and this is happening, and then you just simply say, we don't need to know the equations. Of course it's valuable, and we start on top of that, but they have limits and they become complicated. But now with a lot of data set, you can just bypass this part. So this is very important. It looks very simple, but all of these machine learnings, let's again go to these more complicated models. Again, they have somewhere a loss function. Look, they have a loss functions. I think there should be somewhere, for example, I don't know. Yeah, something like this, that you have a loss function, which is a loss of, I don't know, SE stands for, yeah, some kind of errors, right? They calculate these errors always. So you don't decide about these complex things inside, you just say what you want to see, and that's it. And most of the machine learning models work like that, and this is because of that, it's very essential. So, but then we start with linear, and definitely you know that this doesn't work, right? I just want to play from now on with this linear regression, right? So you will see that how this is changing. You can play with that. Again, you can use some kind of grid search, for example. Just simply say what could be the range of A and B, or alpha and beta, for example. Let's play with that. If you have a small data set, you can just generate one, calculate a difference, and so on. But this is a very exhaustive way, and usually don't do that. So I just calculate this. I just have these linear regression models based on A and B, and then I have a function which is called calculate loss. So that's it. And then I do here like some kind of grid search, and then it tells me this is the A star and this is the B star, because the loss is minimal. This is a very exhaustive way of search, but there are always some kind of optimization. So the whole field of optimization, in principle, here that I said here we need always optimization, it's about these things. There are lots of people who are working in this field, how to find a fast way to optimize this kind of loss functions. And in principle, there are few people, there are a lot, but by ratio, there are few people, they say there is no such a thing as machine learning. It's just about loss function design. So this is called energy-based models. They say you can stack a lot of layers of operations together. As long as you can calculate the loss functions and optimize the loss functions, the model learns somehow some parameters, and it's always good. So for any applications, think about it. You have data sets, put them together, create a loss function, optimize it, it works. And that's all, but nothing more. So, but then if you go to the details and so on, there are lots of algorithms. So you can call it clustering sometimes regression, sometimes nonlinear regression, and so on and so on. So this is, the whole seminars are about this, but I think these are very fundamental, nevertheless simple. So this is like, imagine now without interactive play, it says that this is the best you can get with the linear regression, right? So now you say, what if I just say, maybe my data is not linear? What if I have nonlinear? So it simply says, okay, just you can extend the order of this, your polynomials. So for example, I have degree m, and then in principle, you can do it by, I would say by hand as well. If you just multiply each row to this and plus epsilon, which is the error, you get this. See, this is the matrix format of this. It's extremely, and this is expansion of that. So if you have order of, for example, n, in principle, this is a kind of a higher order polynomial, but when you expand it like this, then in principle you can assume that x1 is your data observations, and x1 to the power 2, and this is kind of following the so-called Taylor series. And in principle, you can assume that now I have m plus one-dimensional data sets. And then again, train a linear regression. So this is a polynomial more than degree of 1 regression. In principle, it turns out that is a multiple or multi-dimensional linear regression. But nevertheless, its result looks nonlinear now. So now I'm not going to implement this. Use scikit-learn. Play with the scikit-learn is amazing for this basic and classical machine learning methods. So imagine now you have this data set. Definitely if you use a linear regression, doesn't work, right? You see that. So now we are playing with the degree. Now I just say with the scikit-learn, I have this function, which in fact is calculating this matrix. I have one dimension, and then in principle there is no interaction between x1 and x2. Always is x1, for example. This is the observation, right? x1 or xyz, for example. Here we just have x and y. So with this function, it just expands this series for you. So you do that and you say poly, and then the degree, you decide about it. This is again meta parameter, like the bandwidth in the kernel density. You set it, and then you just say now poly fit transform xtr to something else. Now I have a higher dimensional data. From this I go to the degree m, and then you train a linear model, linear regression, and then you fit the model. So this is super easy to use for any data set, and then you just predict. So let's do it now. This is if you use degree 1, it optimized, right? And definitely you say, okay, it's not cool. If you use 2, it fits easily the functions, right? And if you use 3, 4, 5, I think it's a bit slow. Let's increase the size, and you see it creates a very strange behavior. And after a while, they are canceling out each other, so the result is not that good. When you have a polynomial of degree 98, for example. So again, as a meta parameter, you know that, for example, this is good. So you should ask yourself that in most of the cases, if you have like high dimensional data, you don't have this visualization easily, right? So you can't visually say this is like degree 2. So you need to know some terms like cross validations or out of sample predictions. This is where you set a degree, for example, you tune it, and you tested your test data which you have never seen before. So you separate your data to test and the training and validation, for example, sometimes. Think about it now, for example, you have test and training. You train this with degree 2 and check it with the test data, you see how good it is. Then you go to degree 3, 4, and so on. This is the way you do in machine learning. So you always need to test your method by some new data. Cross-validation is when you don't have a lot of data, so you just divide your data to random folds. Let's say 5-fold cross-validation means that you divide your data to 5 sections. You take 4 of them or 3 of them, train a model and test with the 2. And then you randomize again. So this is the way you test. Because here we have the visualizations, right? But usually we don't have. But then, as I told you before, these methods have limits. For example, they can't get better after a certain threshold. You will see that there are much, much better methods. Like for example, as a keyword that we will discuss about this, for example, there's a method called ensemble methods that we now randomize linear regressions. Imagine now, for example, you have one linear regression for all of your training data, but what happens if you take sample of your data and for each sample train one linear regression? So in principle, if you have 100 samples, your model is, you have 100 linear regression for your data, for your training data, and then you can combine them. So it means like you have a lot of biased linear regressions, and then it's always like they're voting together. Instead of having one line, you have a lot, and this is called ensemble. So you will see that, for example, one of the best methods that I've seen is called random forest, that you use ensemble of decision trees. Decision trees is something like linear regression. It's a very weak method, but when you combine them together, like a democratic setup, when they vote together, usually the result is better toward that goal. But I'm not sure for democracy is always the best. So then, but here, for example, you have limits. For example, you can't get better after a certain threshold of, for example, degree, for example. They suffer from the curse of dimensionality as well, because always they are trying to find the functions in the space of the data. So you need, there's a term again that we will talk about it. It's called feature transformations, that sometimes you can transform these, for example, 100 space to 5-dimensional space, and then there a linear regression works. But linear regression itself can't do that, right? For example, all of these deep learning applications that nowadays work easily is because they automatically transform the space to a lower dimensional space, and in that space they use linear regression. That's the whole idea of learning. So it's called representation learning. Here your representation is fixed, and because of that it has the problem of curse of dimensionality. And the training time increases exponentially by using higher polynomial degrees. You will see in a moment. And then always it assumes a functional relationship between variables. This is another fundamental problem, because here you learn a functions. But what if there is no function at all? So then you're imposing a lot of limit to your models. You can relax this, and you will see that this will, in many of the models, you don't have these assumptions. For example, there's a model called local linear regression that simply, like this data set that you have here, like here, you know that if you fit linear regression for these, one here, one here, one here, one here, it gets better. So in principle, you divide your problem. So you can do it again automatically. And this is called local linear regression. And I think if you want to read books, there are a lot of books about this, because this has been the discussion of statistical machine learning for at least, I would say, 100 years. So there are a lot of work in this area. But it's good to know the foundations, and the rest are like minor improvements, I would say. And then structural assumptions that you have. And so in principle you can't change the parameters easily. You need to add another block of modules. So now here I just want to show you very quickly what does that mean, that it doesn't get better after threshold. For example, I think here you see that I have this simple problem. I think again one-dimensional, and then by increasing the degree I calculate the median error. It gets better, and after a while it's stable, and then it even gets worse. So you can play with that easily. So here is a way you can see that in terms of meta parameter space, again I'm referring to this initial a bit vague space. It's always like that. Now you have a parameter space, which is the degree. So you, as a designer of this model, you just need to design what would be the range of parameters, and the rest is by the model. So you just relax, but then you're still responsible. It's not like that everything is automated. So yeah, that's it. And then you have, for example, another problem. I would say, let's use a real data set. For example, here is a data set from real estate of Switzerland. I think you have these values: rental, zip code, type of the apartment. Then you have this kind of categorical data. So always there's one of them is 1, and the number of rooms, year of construction, and the living space, and the location. So you want to see how good you are in predicting the real estate price. And you can simply remove this part and don't think about it, and then just add a lot of more dimensions, and you will see how it works. So here I just want to show you that the degree, because so far all the examples were one-dimensional x. Now here we have, I think 2, 4, 5, 6, 7, 8, 9, 10. I think we have 11 dimensions. So if you increase the degree, because these in these polynomial functions they need to multiply to each other. So you have from degree 1 you have 11, from degree 2 you have 66 variables. So the space, and then you have the curse of dimensionality problem. If you increase the degree to 3, you have 286, and if you go to 4, it's 1000 variables. So because of that, for real scenarios, usually it sucks. So you see that it has this exponential. Yeah, because it's always good to start with linear regression. It's very easy to use, but you will see that it's not working. And it's good if you want to write a paper, you just simply say, look, linear regression doesn't work and my algorithm is better, of course. But it's good to, I mean, yeah, it's linear regression itself is simple and it's not that strong, but the concept is still there. So this concept of inverting the game and just asking what you want to see, it's always there in machine learning. And I think if you get this idea, there is no problem with learning new algorithms, because they're all marginal, I would say. So then, as I said, if we don't have non-continuous domains, what happens? It doesn't work very well. You see that, again, you can visualize it, but in reality you don't have this visualization in high dimensional data, but you see that it doesn't work. It tries its best, but it's not working, right? So I think I pushed it too much. You didn't need these observations. So this was like this session. I tried to explain to you this fundamental idea of learning. What is learning in principle, or estimation, and then what is, for example, this density estimation. That I implicitly mentioned the idea of unsupervised learning, which is when you don't have a target. In fact, you have a target always, but you don't have one of these dimensions as your target. This is called unsupervised learning. And when you have supervised learning, is that when you have a target, or in a way you're conditioning your result to observations. So then you have these linear regressions, or in principle least square methods. You will see that in later next sessions. For example, we will talk about PCA is the same. In clustering methods, you always have the same story. You need to think about this stuff. So I think that's enough for today. I think I try to always beat you 1 over or less, or not more. And if you have questions, for example, if you work with this, because I think it's really good if you play with the codes and then try to understand it line by line. Because if I explain it, even if I did this like a few months ago, sometimes I make a mistake. And it's when you have this visualization, sometimes it's misleading, because you just say, oh, I got it, but you don't get it in fact. So if you play with these codes, I think I will check always the amount of the new topics or new keywords that I will add. Because of that, I don't go more than 1 over. But if you get involved, I'm pretty sure that we will have a lot of more questions. Otherwise, it's like enough, I think. So there are lots of extensions to this problem of regression, and then we have local polynomial regression. I explained it briefly. Then you have nonlinear regression, curve fitting. This is a field, for example, in mechanical engineering or electrical engineering. We have this notion of curve fitting, which is very common there. And then, for example, you have the idea of basis functions, and which is common in control engineering. And then you have generalized linear models that are trying to improve a lot of things. And for example, just go there, play with that. For example, these guys implemented everything. So it's called GLM, it's a library. Then you have OLS, then you have ridge regression. They're all interesting topics, why they do that. For example, this is the idea of regularization, and this is important in, like, when you saw here, for example, it was like two functions. This is like this case that I showed you, that what if you have several of these momentums together, because they are talking about different things. And then in these modifications, always about that, how to control, for example, the weight values and so on. And they have a rich history. I mean, if you read about them, ridge regression, I don't know, lasso is important, many people use that. Yeah, and then there are a lot, you know, multitask lasso, elastic nets. Most of them at the end have the same problem, as I told you, like increasing the degree increases the time complexity, then they have curse of dimensionality and so on, but they all have small contributions, which is important to know. I mean, if you want to play with the data, you need to get the concepts, and then you need to quickly understand what are the differences, but these models are already implemented. You don't need to spend a lot of time to just implement it. So you just, it's always like that, you just get the data, train and fit, and then you test, and then you need to know what is cross-validation. So this is a kind of a data-driven modeling in practice. There are many people outside nowadays in industry, in different companies, competitions, they just use this. And then, for example, I use this on a server now. I have a server which is for this real estate price prediction. I train a model, and then you deploy this model to a server, and then later people come, like I can show you quickly, and I will tell you in detail. For example, this is very, very close to the market. I think, if I'm not wrong. So for example, here, for example, this real estate data, I'm crawling this data every day. Then I, in principle, because I stopped this for a while, we were looking for investors for this. For example, you crawl this data, you get the data, you clean the data, and then you use any of these methods, which is good. And then I use scikit-learn, for example, and then I deploy this model on a server, which means the train model. It's like an expert now. So here now you can go and say rents. For example, apartment, you remember here we had these parameters, right? This is exactly these parameters. Now you do it through kind of step by step. These are designed. So you just add the zip code. You can add your house information, and I will save it my database as well. You should know that. And then at the end, I will tell you the price, for example. So I don't want to go through it. If you want, we can check with, for example, my house is here. For example, oops. Straw. So I live here, for example. Oops, I think it's ground then ground. So it's that easy. Look, this form is again these values. So you just need to do that. Everything is here. You can do it. So it works. Now we just say number of room 2, which floor 2, I don't know, living space 80, year built 2000, last renovation. So I hope it doesn't. Oh, okay. It says the price of the house, for example, to 2000 something, right? So this is running now in principle. For example, I don't want to brag, but I mean, this application, for example, is not for free available, right? Because there are lots of companies in Switzerland, for example, that you need to pay them, and they say we are the expert in this field, and we tell you what's the price, but you should pay like 100 to just give you a report what would be the estimated price of your house. But here with this machine learning, data is for free, but of course you need to know how to get the data. I can show you in one session. I have upstairs two computer which is always crawling. So you get this data in a daily basis, you clean it, and you simply just need to know this concept, for example, you just need to know what is scikit-learn and then implement it, and then the rest is engineering, right? And it's not that difficult, but the concept is beautiful because if you know this language, you can implement it on a server, and then now, for example, if you have enough marketing, you can say, okay, I give it to you for like $10, for example, instead of 60 or 100, or even for free. Then you need to know the storytelling, for example. The next steps are different. So I just wanted to show you, and then in one of the sessions I will try to show you how to deploy the whole things from zero, the full stack development. It's easy, and this was my first web application as well. So it's that easy. You just need to learn the concept, go through it, and this will take a few months. And this is the crazy thing that nobody believes. And many of these engineering applications is the same. You have researchers like these people who are expert in this field. They're working on that. They try to optimize something, improve something, and so on. But of course, not everything. But if you have this kind of problems with this view from machine learning and data-driven modeling, you go there, you say, wow, this is an application. This is already implemented in scikit-learn or TensorFlow or whatever. You just need to grab the data and then train the model, and that's it. Where in the classical way, they might try to, for example, find like this example of this astrophysics example in 19th century. They were struggling how to make the models of the new planet, and then it should be based on some Newton's equation or something like that. But this guy said, oh, now we have this technological advancement, we can measure that, so let's fit a model. And then it was good. And of course, in many cases, it's not good, for example. Then you need to improve it. But this is it. I think from now on, gradually we will go through these applications, and I will try to explain to you different things that I know, and I try to read new papers and then add new algorithms. But that's it in principle, and that's very generic. And I'm pretty sure, again, I try to make it a bit provocative. If you have any problems, we can discuss, and then we can see how we can translate it in this language, and it works. And maybe at the end you can say, okay, the problem I'm working is not in this field, or I'm working on something completely, for example, subjective. It doesn't make sense to use machine learning. That's totally fine. But in a lot of applications like this, like real estate price estimation and so on, you can do it. So this is totally disruptive, and this will, I think, happen in many fields, including industry and university and so on. So yeah. Just go there and check these libraries, and then Stack Overflow is amazing. Just ask your questions, and then you will find it. Yeah. Thank you. If you have questions.
I have two questions.